All right, well, welcome back to Lean Together 2026. This morning we're going to begin with Sofia Rodrigues and Markus Himmel of the Lean FRO, and they're going to be telling us about the standard library. So please go ahead.
Thank you, Jerry. So Sophia and I are going to walk you through some new developments in 2025 in the Lean Standard Library. Before we start with that, maybe let's quickly go over what the Standard Library actually is. So the Standard Library is part of the Lean core distribution. That means that everyone who installs Lean automatically gets access to the Standard Library. And really, what it does is it makes Lean into a fully featured, general purpose, high level programming language. So it contains all of the things that you would expect to be there in a programming language. And many of these things that fall under this are useful for mathematics. For example, you have, for example, things like the natural numbers, and then there are many other things that are not really useful for mathematics, and we see examples of both. And one of our principles is whenever such a thing comes up, which is useful for programmers and mathematicians alike, we want to make sure that it really serves the purposes of both of them. We don't want duplication, and we don't want to favor one over the other. As for where you can find the standard library in the Lean distributions, we have this module and also namespace called std, which contains the standard library, but also we have the root namespace and the init module, which contains things like the natural numbers. And both of these are the standard library. And there are things in init which are part of the standard library and parts of init which are not, and most things in std are the standard library. This is growing rapidly. In 2024, we ended with around 100,000 lines. We tripled this in 2025, and this trend is continuing. So development really is happening quite rapidly. And this is being done by the standard library team at the Lean FRO, but we also receive some really great contributions from the community. I would like to especially thank Robin Arnes and Johannes Tantor, who have had many contributions, which were really amazing in 2025, but there are other great community members from whom we have received great contributions. You can have a look at the file doc.std-vision.md in the Lean4 repository. This is where you can find an overview over what the standard library is, where it's going, and how you can also contribute. And now let's go through some highlights of things that were added in 2025. The first is really a continuation of something we've been working on for a long time. Most of you probably know from the start, Lean4 has shipped with lists and arrays, and we then started adding more data structures and containers. And two of the most important ones are our implementations of hash tables and self-balancing binary search trees, which you can find as std hashmap and std tree map. And what I want to stress here is that these are really supposed to be high quality and things that we want to be used. And so we're committed to making them so good that you can really use them in your real project. So we're going to provide all the variants that you might require, for example, sets or dependent maps where the value depends on the keys, or extensional versions of these data structures, or versions that you can use in nested inductive, and so on. And we're also providing all the operations that you might want and all the lemmas that you might need. And this means that for each variant, we have more than 500 lemmas, for some variants, even more than 1,000. So these are really things you can use in your real projects. And we are continuously working on adding more things, and you can expect this to continue in 2026. Next, I want to talk about iterators, which were a new feature in 2025. What you get very often in functional programming are these kinds of data processing pipelines. So here I have some function which starts with an array, and then maybe it throws away the first element, and then it performs some operations on the elements, and then it does the filter operations. And finally, we ask whether all of the remaining or resulting numbers are greater than 25. These kinds of things come up again and again. But the way this is written here, which used to be the only way you could really do this, is actually quite inefficient, because whenever we do something like drop or also filter, and sometimes even with map, we actually create an entirely new array. And in the end, we just iterate over the final one, which is very wasteful. What we really would want is we loop over the elements of the array A once and do all the necessary operations in line. And luckily, you now don't have to rewrite this entire function to do this loop operation. What instead you can do is you go over the iterator. So you take a.iter, which returns an std iter net, and std iter is our iterator or stream type. And now this actually compiles to the efficient loop that you might want. And it does this by not working on arrays, but on working on these streams instead in a completely general way, which also means as long as a container or a stream exposes this std iter interface, you get a completely uniform interface that looks the same wherever the data you're working with is coming from. And especially if you're implementing your own collections or streams or containers, you simply have to return an std iter, and you immediately get access to this entire infrastructure that is now part of the standard library for manipulating data. And this includes a long list of lemmas. So if you're implementing a container, instead of doing all of the operations by hand, now by working off iterators, you get a lot of functionality essentially for free. And once again, this is quite flexible and general. You get both finite and infinite iteration with good support for both. And you also get monadic iteration, which is also very useful, for example, in metacode. Okay, for the next feature, we have ranges and slices. So some of you might remember the old range notation, which has existed for basically forever, which used this square bracket with the colon in the middle. And this only works for natural numbers. So you'd use this, for example, if you wanted a for loop, which ranges over some numbers. But very many people rightfully complained that this only works for natural numbers. And now we have a very general answer for this with a new syntax. So we have a fully polymorphic range notation with these 3 dots. And once again, there are many variants of this, depending on whether you want the left or right bound to be included. And you can even have infinite bounds with an asterisk. This is not shown on this slide. And the way this works is that depending on which type classes your type implements, the ranges gain capabilities. So, for example, if you only have a less than or equal instance on your type, then you can already check for membership in closed ranges. And then if you implement additional type classes, you eventually gain iteration. And from there, you can do all of the things that you might expect based on the old range notation. So for example, you can use this in for loops and things like this. And you can see here that then, of course, you also can benefit from everything that's in the iterator library. For example, here in the last example, I'm showing the step size function on iterators, which then allows you to essentially build a range with a given step size. We also have slices, which are somehow a combination of just a container and a range. And this allows you to efficiently build views on data structures restricted in some way. So for example, if you have an array A, then you can take the slice from 1 to 5, and then you get a view that consists of only the indices from 1 to 5. And similar, but not quite the same, if you have a map with integer keys, then you can take a slice of that map to have the version of the map that only consists of the keys from 1 to 5 if they are present. And both of these are very cheap to construct because we basically just store a pair of the map and the ranges. And of course, this syntax is again completely extensible, so you can override this for your own data types and make use of existing infrastructure that we have built for this. Okay, the next feature I want to talk about are strings. Strings traditionally were a bit of a touchy subject because on the one hand, you want to think about them as a list of characters, but on the other hand, Lean being a programming language has very strict requirements on how efficient we need our strings to be. We need strings to be really fast because otherwise Lean is slow, and this not only affects things like Lean compilation, but also things like autocomplete. And for these kinds of things, which every one of us interacts with potentially thousands of times a day, really every bit of performance matters. And many people at the Lean FRO have been working really hard to make sure this is fast. So representing a string as a list of characters is certainly not going to cut it. But on the other hand, storing a string as a UTF-8 encoded byte array puts you in the difficult position that you then have to reason about UTF-8 encoded byte arrays. And finally, so for a long time, there has been this large disconnect in how strings work at runtime and how they are represented in Lean's logic. And now we have finally resolved this disconnect by basically sitting down and doing the hard thing that we have been putting off. So now strings have been redefined to be byte arrays that are valid UTF-8, just like at runtime. And to make this possible, we of course had to verify UTF-8 encoding and decoding. And this is really a nice example of how by working on a problem bit by bit and adding things over a long time, you can really achieve quite non-trivial things, because this verification of UTF-8 really fundamentally uses the work on bit vectors that both the FRO and the community have been contributing to for a long, long time, and also the verification of unsigned fixed size integers that again builds on the bit vector theory. So that's very nice, and we're proud that we have this new definition of strings. And on top of this, we were also able to improve the string API that users see. I just brought 3 snippets, which I'm going to explain very quickly. In the first one, we once again have such a data pipeline where we restrict a string to a substring and then check whether the substring starts with something. And here you can, or basically you don't see that in the background, we're actually going through a new type called string.slice. So dropping 2 characters from a string, for example, doesn't actually copy over all the characters, but it just returns a view on a smaller string. In the second example, you can see our new polymorphic string searching and matching infrastructure. So you can here check for both a substring as a string and for a or for a character that satisfies a certain predicate. And when searching for a substring, you also get an efficient Knut-Morse-Pratt-based linear time string search, not a naive quadratic time one. And this is also the first time we've had this in the standard library. And finally, in the end, you can see many of the things I talked about earlier interacting, because strings now also expose iterators both over the positions in the strings and the characters in the string. And you can use that to implement certain operations on your strings quite efficiently. Okay, quick interlude before we go on with new features. What about quality? So we want people to install Lean and be immediately amazed by how well everything works. And for this, we need the standard library to be really, really good. And there are many ways you can try to make your library better. Tests and linters are really important. We've seen MathLab especially have some amazing results with their linter infrastructure. But we are going to go even further to catch all of those things that tests and linters have difficulty finding, for example, completeness or certain consistency issues. And for this, behind the scenes, we've been building a tool called Growth, which basically takes the form of an interactive living design document that evolves as the library evolves, and that contains all of the design decisions and tests and tables and other information about how well we're actually following our own design decisions. And I don't have time to talk about this too much today, but we have built this. We are currently rolling it out in the standard library. You will hear much more about this in 2026. If you do not want to wait, you can also check out my presentation at the URProofNet workshop on proof libraries, which you can find on YouTube, where I say more about this. And with this, I'm going to hand over to Sofia, who will walk you through more exciting things in the standard library. Sofia, are you here? I see Sofia in the room. I hope she...
I've just asked her to unmute. I'm not sure. I get the feeling that she was having connection issues or something because she just disappeared for a moment.
Yeah, let's maybe give her a minute to try to reconnect, and if not, I can take over her part of the presentation.
Okay.
Okay. So you can hear me now?
Yes, we can hear.
Okay. So so now I present some things that I've been working on with the rest of the team. So these are the topics that I will present in the next 15 minutes. So the first one is about the date and time library that is available in the std.time namespace. And then the concurrency library that is located both in sd.internal data sync. So it's an internal library right now, but soon it will be released to be just sd.async. And then the other one that is available in sd.sync that contains some data structures and some stuff that is useful with the sync library. And then on top of these things, the last library that is the HTTP library that is still internal too, and it is still a PR, but soon it will be released too. So these are the topics. So just to start, I will talk about the date and time library. So a lot of languages have the time units as it. In Ling, we do not want to have simple types as for everything. So we have in the date and time library offsets and ordinals both for a lot of time units. So seconds, minutes, hours, months, days, years. All of these types, these time units are represented as types, and both as offset types that are represents time spans and some shifts in time, and ordinals that are used as components for other types like playing day times. They are used to represent a position in a time unit. So here we have a simple snippet that we can show the minute offset and hour offset, and you can perform some operations with them that results in some other types. Like if you sum a minute offset and an hour offset, you have a minute offset with the conversions done. and then a minute ordinal on the second line. Then we have the timestamp and duration that are two related concepts because the timestamps represent a single point in a time, and the duration will represent the span uh, between two timestamps in some sense. So in the first line, we can have the timestamp, the current timestamp that we can get with timestamp.now. And in the second piece of the code, we have uh, we try to calculate a duration from these timestamps. So if you subtract two timestamps, you get a duration. And so in the first line, we get the timestamp, the current timestamp, we sum 50 seconds, and then we subtract and we get the representation that is it's 50 seconds of duration between these two timestamps. On top of these concepts, we can build some other types. So in the library, we have 5 types that are the main types for calendar time. But here I'm using only 4 types because they are the essential ones. So the first one is the plain time that we can build from a lot of functions. In the first line of the snippet, we can see that we are building with a function called of hour, minute, and seconds. So we can use these 3 components that are represented with the ordinal types, and then we can build the plain time. But in the representation of the plain time, we have a different notation that has parentheses, and this is the macro that can build the same exactly structure. So these are the 2 ways to build it. You have more ways to build the same structure, but here I'm showing just 2 cool ones. So the second line we have we try to build a plain date out of days since the Unix epoch. And in the last one, we build out of timestamps. So the function names try to be um, really specific, so we don't have a lot of room to errors, and we have a lot of ways to create these things. The zoned datetime, that is the one that is not in the snippet. It's a plain datetime with zone rules. So it contains the time zone and the transitions, the historical and political transitions between these things. So daylight saving time and other stuff like that is inside this type that's called zoned datetime. And with it, we can parse and format these things. So in the last snippet, we create a zoned datetime for using my time zone, that is America São Paulo, and it returns an IO of zoned datetime because it needs to fetch from the IANA database the zone rules and the other stuff, and then we can format this using this format that is in the last line. We have a lot of formats already in the library. You don't need to write yourself a lot of these formats, but you can do if you want. So in the uh, blue line, we can see the result of this formatting. Then after the datetime library, we have the concurrency library, the async library. So it's built on top of libuv. So libuv is a runtime. It's an event loop for that was mainly used for Node.js and Julia, that are 2 languages, and it enables us to receive events with callbacks and other stuff in the C++ side. But we try to transform it to another thing, and then I will show you the async monad that just abstracts on top of libuv. But but we added support for a lot of other things like TCP, UDP, DNS, signal handlers, timers, and process and system information. So that's all we have right now with libuv, but we can add a lot of other things later with, I don't know, file systems, file system operations, and other stuff. We have a code example here that has a lot of this concept. So we have sockets. So in the second line, we create a TCP socket server that binds on a local host. So it's the 0000 address. And then we have a signal waiting for a SIGINT signal. And then we have this while loop that accepts both a new connection, so it waits for a new connection, or a SIGINT signal. So depending on it, it will uh, create a new, it will call this function called background that will launch a new task that will send this message after 1 second to the socket. Otherwise, it will shut down the server. So if the person just triggered a SIGINT signal, it will shut down the server, break the loop, and stop the execution of the program. So that's it. The selectors are a concept for waiting for a lot of these events at once. So you can wait both for the accept selector and the SIGINT selector and do it efficiently with cancellation. And then we have the sync monad. So we used the sync monad in the last example, but here I'm showing these with some combinators. So we have combinators like concurrently and race that do their job. Like in the first line, we concurrently wait both for the results of async sleep and of 1 second and async sleep of 2 seconds, and it takes 2 seconds. So it's doing it concurrently, and the result is 2 units. In the second eval, we have the race that waits for the first one and discards the second one, but it does not cancel the operation. And in the third one, we have a worker that's working on this other type called context async that has a cancellation context. So you can cancel the operations in a cooperative way. So you need to check for cancellation. So in the worker function, we wait for 5 seconds, or we wait for the context async to be done, and depending on the result, we return a different string. So slept or cancelled. And in the last eval, we call this. So we create a new cancellation context. We run the worker asynchronously. We wait 2 seconds. We cancel this function, context, and then we await for the result of the async operation. And then we get that it took 2 seconds. So it waits. It had to wait 2 seconds to cancel the worker, and then it has it in cancelled. So yeah, for async, that's it. And then we can move on to the HTTP server. So the HTTP server is built on top of async. So it's a way to use the sync library and check for the API and check if we need something to improve it. And it uses a lot of other concepts of the STD too. It is based on Hyper, the Rust library for HTTP that's really low level. So here we don't have routers, we don't have a lot of things. And currently it supports only HTTP 1.1. HTTPS is coming soon with another PR that adds OpenSSL tooling. And right now it's still a PR. So we need to merge it, but I have to fix some small issues first. But we have something working. It's working. I think that it's really cool right now. And this is a snippet that shows a bit of how it works. So in the main function, we use the async monad, but we block on the we transform it in an IO monad by blocking it. So we can use this function called async.block that just makes an async monad into IO monad. We serve the server in the local host, and we wait it to shut down. So it will block until someone tries to shut down the server. So you can shut down the server gracefully by just like calling shutdown, and it will cancel all the connections. It will send a response that says that the server is closing. It's closing, and then it will just finish your program. And then we have the handler. That's a really simple function that receives a request and returns a response in the context async. So it's really simple. It checks for the method, it creates a response, and then it collects some string. And that's it.